So let's start. It says equation 4.3, which is this one, Newton's law of universal gravity. Gives a mathematical relationship describing the magnitude of the gravitational force between 2 points. So what this means is G is a constant. I'll look that up in a little while. I don't remember.
6.67 times 10 to the negative 11.
Just off the top of your head, thank you.
Yep.
You remember the unit?
Newton.
M1 and M2 are the masses involved. And R is the separation, there's separation between them. This is a constant proposed by Newton and discovered at a later time, as your text says. I believe it even gives a name. But it's an empirical thing. It's something we've measured. And to my knowledge, we don't have a way to derive it just using math. We have to measure it. But it is a constant universal. Okay, since it's a force, though, it must also have a direction. How can you state the direction for the direction of the force in a way that is general enough to apply to any two masses, but still specific enough to be meaningful? So we got a variety of answers here. What do you think, Morgan?
The pole is towards the other object.
That's a good way to say it. So if you've got two masses, here's M1, here's M2. M1 experiences a force this way. M2 experiences a force that way. It's an attractive force. And so we might describe that as, you could just say that on a line in between the two. It's attractive on a line in between the two. Or one way that we would do it in math is to use this little guy, which will make some people from last year giggle perhaps. Cringe perhaps too. That's called a unit vector. We would pronounce it, or we would say it, r hat. And all it is it's a vector that gives us a direction. And it says it's pointing along the radial distance direction between the two. So this is that direction. It doesn't affect how big it is, the magnitude of the force. It just tells us it's a radial thing. Okay, that was a lot smoother. Good. Your brother, Candy, got me pretty good on that one day.
Oh.
He punked me pretty good.
I'll ask him about it.
There was a lot of discussion. One person in particular was getting really frustrated trying to understand what this meant. And I turned around, and your brother, who sat right up here, said, "Wait, could we go back over that R hat?" And I just sort of, and I started talking, and I looked around, and he's just grinning. It was good times after that. Okay. Second question. The Earth and Sun have a gravitational attraction, but are not point masses, which is what this assumes. What simplifications do we have to use to make this apply? So here's the deal. This works for one point mass to another point mass, so extremely small masses. And if you picture the Earth and the Sun, each little point in the Sun interacts with each little point in the Earth in order to do that. Both are roughly spheres, but not quite. So their attraction is a sum of all of these points attracting all of these points and vice versa. If we used calculus, which of course Newton was developing at this time, we could do something saying that we would sum up, we'd still have the g over r squared, but then we'd have some sort of a dm1 for the sun, dm2 for the earth. We'd have to do a double thing, and we'd have to go through all of the distances that separate each of these points in order to find out the actual total force. Or what simplifications can we make to make this maybe not quite as precise, but much, much easier?
Simplify that each sphere has an evenly distributed mass.
That's one thing, so we don't have to worry about if this point mass is a little different than that one, and so forth. So that's one. What's the there's another easy, good simplification. The r point masses. As it turns out, if we work this out, this calculus, with everything being uniform, we get no difference in the outcome of whether this is a giant star or a single point with the exact same mass. So we always assume that it's a single point at the center of the two bodies that's attracting it. And we, by assuming that they're uniform, we can do away with all of this right here and just use Newton's equation. And it's a very, very close approximation because the distances are so big usually in between things. It's also interesting to note, I think, that let's say that you get your drilling machine, Gesundheit, and let's say that this is Earth, and here's its center, and here's you. And you tunnel down into the Earth. Well, you are really into this sort of thing.
You're also burning.
Yeah.
You're in the mantle at this point, you're done.
Well, yeah, I suppose you would be. It's probably molten. Let's assume you've got some good boots on. Now, the interesting thing here is you would have to, in order to find out how much gravity was affecting you at this point, you would have to take each point of yourself. Maybe you could assume that you're a single point mass, but then you'd have to get the effect of that point over here, and this point over here, and this point over here. Some are closer to you, and so they would have a greater effect than the ones farther away from you, but there are a lot more farther away from you. And the interesting part about this is if you sum up all of these, and it gets a little hairy with the integral there, what you find is it's the same as if you were just standing on whatever's inside of you, and you ignore all of this out here. So it's just like you're in a smaller, hotter planet with boots. I just found that interesting. We're not going to do the calculus. That's just an interesting result, I think. Okay. Now, if a planet were too distant or too inhospitable to land, and this is like some of those exoplanets that we found would fall into this category, we can't get there. Not with what we know now. How can we measure how much the acceleration would actually be? Because when we've seen some of those, and we saw one or two mentioned in the video, and we talked about some that's, oh, this one's 2.4 times the Earth, and so we think it'd have gravity like this. How do we know? How can we figure out what the acceleration of gravity would be, and then make it easy for us to calculate our weight?
So the gravity, the acceleration would be g times the mass of the planet divided by the radius squared.
Why?
Well, because pretty much it's just acting on the surface and not on, pretty much it's acting on the objects on the surface of the planet.
Okay.
So you're taking the radius of the planet because that's how far away the center is from the objects that it's acting on. And that's...
So what you're saying is, if you were standing on the planet, we could use this. You'd have g times the mass of the planet times your mass over the radius squared of the planet. But now, how does that give us what g, the acceleration, would be?
I changed half to mass on acceleration, so then it would be M2, or I don't know what.
MU.
MU.
Times the acceleration of gravity in this case, so A or G or whatever.
And then you could divide both sides.
Yeah. So the MU is the same on these, so that leaves G to be the rest. So the mass of the planet here divided by the radius of the planet squared gives you what the acceleration is. So even though we can't visit it, there are ways to measure the radius, and in this case with the exoplanets, we're measuring how much light does it block from its sun. So we get a good idea of how big it is. And then I am not fully aware of how we measure its mass, but there are techniques to do that. Certainly if it's a big planet, we can measure how much the star wobbles as it goes around, but a little planet like Earth, I'm not sure we can measure that precisely enough to do that. But there are ways. So if we can get the mass of the planet, then we can do that. Okay, let's switch a little bit now. So that's a lot about gravity. We're going to be studying orbits next week and how some of the early astronomers figured out that the Earth really isn't the center of the universe, let alone even our solar system, or vice versa, the solar system or the universe. And part of that is understanding circular motion. So this says, describe the direction of an object's velocity while it travels in a circular path. So let's say we've got our circular path here. We've got something going counterclockwise. How would we describe its velocity at different points, say those two, but still make it meaningful? A lot of people said, oh, it's changing all the time, which is true, but we can be more meaningful than that.
It's tangential to the circle.
Right. So if we take a velocity of the object as it's going around, the actual velocity at any point is tangent to the circle at that point. So we have VA, and then as it turns around, continues to turn, it's still tangent there. Like so. It might not change its speed, so the length of that vector might still be the same, but it is tangential. What about the direction of an object's acceleration? Yeah. Always pointing towards the center. So there's got to be something changing it and making it move. And so for this, most of you probably remember, we've had this out before. When I spin this string, the string is what's applying the force, and the string always pulls. I'm not going to let it go, most likely. And as one or two people noted, strings suck at pushing. Okay, so that is there. Now let's picture this as a fast spinning carousel. So this disc is a fast spinning carousel, and we have a shoe out here. That looks like a peanut. What direction is the centripetal force on the shoe? This is one that was actually, although a lot of people can picture it, actually misanswered a lot. Same as acceleration. F equals m times a, and they have to be in the same direction. So the force must be in towards the center. Several people got very close to the force. Zach, I believe you're the only one with the extra detail. What force is supplying that? Static friction. So a lot of people did say friction. Specifically though, since it's not sliding, it'd be static friction pulling that in. If static friction were broken and the shoe suddenly started to slide, what direction would it go? Let's say that all of a sudden it's frictionless. Okay, and what direction is that?
Tangential.
Tangential to the circle that it's on. Can you make a sign or something in the direction that you're
I think
picking?
it'd be like,
Yeah, down and to the right, right? It'd keep going straight. No forces, things keep moving straight. And so another note is that this acceleration and the velocity are always perpendicular. So same thing then with the force and the velocity. So this would be the velocity if it were to break loose and just start sliding. Same thing with Earth. We'd just continue on in a straight line if for some reason the sun suddenly wasn't there. I can't imagine any way that would happen. Because if it exploded, like somebody blew it up, well, the center of the mass would still be where the sun is. So we'd still be going around that until we were vaporized. Then it says, text states there's only one speed that a satellite can have if the satellite is to remain in an orbit with a fixed radius. Does that mean that all satellites orbit at the same height? No. That would make an awful mess up there. It's not necessary, so if they're going to have different radii though, if some are going to be farther than others, what has to change about them? Speed. Mass actually doesn't end up mattering. We'll see why in a moment. Mass is one of those that it'll kind of cancel itself out. It's sort of like friction slowing an object. It doesn't actually matter how massive the object is because the friction changes proportionately. Same thing with gravity here. And then the last one, explain why astronauts are weightless but their spacecraft are still held by Earth's gravity. I think Ben had my favorite answer on that one.
They're like falling, but they don't actually hit the planet, they just miss.
Yeah, they miss. They fall, but they miss. So they are under Earth's gravity. Everything up there is. The moon is. So anything but certainly between us. And when we look at Newton's law here, this has nothing saying that this works until r is a certain distance. What happens though is r gets bigger and bigger. What happens to our force? Decreases. So it gets very small, but it doesn't actually stop. Every other particle in the universe is affected by Earth's gravity. It just gets really, really small the farther out we go. So if we were to look at this, what he's saying is we've got our spacecraft up here orbiting, not to scale, orbiting, and it's actually being pulled, of course. It's got a force this way, but it's also got a lot of velocity that way. So it is falling towards Earth, and it would feel just like you would on, essentially like you would on the power tower, except you wouldn't have the wind in your hair. But then it's also moving to the side. So while it's getting pulled to the center, it's moving to the side, so it continually misses, which, as Douglas Adams noted, that is the secret to flying. Throwing yourself at the ground and missing. Let's talk a little bit more about this stuff, this good mathy stuff. And specifically, I want to look at, we're going to talk now about how do we know what we know about centripetal force and how can we make sense of it. So we're going to take these 2 points again, and I'm going to draw this radii out here, mostly successfully. Okay, and we're going to look at something spinning and moving from point A here with the velocity VA to point B there, the velocity VB. The two speeds will be the same, but obviously the velocity is different because of their different directions. And we've got a radius that we're just going to call R, and we'll call this point A and point B. And I want to find out more about the acceleration. So in order to do that, we kind of have to look at, we remember that acceleration is a change in velocity, which is a vector itself, over time. So I want to look at this change in velocity. And this is, we didn't deal much, or maybe at all, with a change in velocity that is only direction, unless it's going along the same line. So in order to do that, we're going to take our drawing over here. I want to get those apart. Okay, and just for ease of seeing, I'm going to try and redraw that. Imagine I'm redrawing that perfectly to scale. If we want to know what the change in velocity is, it's this thing that connects one velocity to another. This is our delta V. These are all vectors, and that's kind of why it looks weird. So it's not 1 plus 1 equals 2, it's 1 plus 1 equals 34 degrees sort of deal. And then, of course, we have to assume that these two are the same velocity, so I'm just going to, for shorthand, say that V is equal to VA and VB. We're just going to simplify that a little bit. Now, if we are traveling here from point A to point B, we have a displacement here that is of interest to us, because we can also say that the velocity is related to that, because it's a change in position over time. And so there's our delta V, that's fine. And I don't think I need that. Yeah, we're good with that. Now, these two triangles, and if it's all right, I don't want to go through the geometry. This triangle here, this AB, and we'll call it C, is actually going to be similar to that triangle. Meaning that this interior angle theta is also that angle theta. We're going to use that because along with the law of cosines, one of your favorites, I think, which is saying that if we have the three sides, we pick one side that's equal to the sum of the squares of the other two sides plus twice their product and the cosine of the angle between them. Okay, so yeah, that's good stuff. But it, yeah, where did I go with that? No, I'm good with that, but yeah, it is a Friday. We're good with that.
I don't have to go to school tomorrow. I think that's pretty sweet.
That is nice. I'm just looking at this, and yesterday this all made perfect sense to me.
See, that's how I feel every day in this class.
Yeah?
That math
It's
is
like yesterday that made perfect sense. So I'm going to write this down, and then we're going to come to this. Then we're going to come to the understanding together, okay? Because I might have. Oh, I think I got it. Okay.
when your teacher says, I think I got it. Don't worry about your
Well,
mistake.
the idea with this is I want to show you why this is equal to this, rather than just say this is equal to this. And so here's the problem. Losing track of why. But now I got it. I just misread part of my handwriting. I think. So in our triangle, what do each of these mean? Well, we want to look at the distance between these. The distance between these, I'm just going to call the length AB. Okay. I misread my next letter as a V, and it's actually an R, because these two then become the other two sides. Their lengths are both R. So we have an R squared plus an R squared plus 2 times the length of this and the length of that, which is itself R squared, and the cosine of the angle between them. And that's squared. And then I'm just going to gather some of these terms over here. If I factor an R out, this, by the way, is one of those derivations that I want you to kind of pay attention to. You're never going to have to give this back. So if you just want to watch and put all of your brain energy into seeing what I'm doing rather than writing, that's cool. And watch the video if you like later. That's good too. We have, what's left is we have 1 and 1 here, so that's 2. Plus, we still have the 2 there, times the cosine of theta. And we can even, do I want to? Yes, even factor that out, that 2 out. 1 plus cosine of theta. Is that a minus up there, or is that a plus?
I think we need minus, yeah, so
That is a plus, I am, okay, good.
That's a plus or minus sign.
No, it's a minus, isn't it?
Yeah,
I have a minus in my notes, and I just realized that I really need a minus in my notes. Well, see, this is why you don't write stuff down, that's okay. Not this, anyway. Not this. Like I say, this is just hey, where does this stuff come from? Okay. So I'm going to divide both sides by the r. And take the square root. So that would get rid of the 2 squares, but it'd leave a square root over here. 2 times 1 minus the cosine of my angle. Okay, now, yes, but we don't really need it. Okay, now if we did this exact same thing with my other similar triangle with the velocities, we'd get a similar, I'm not going to run through all of this, but we'd get a really similar find here, namely that the far side of our triangle, which we said was the change in velocity, over the length of each side, so that's this side over these, just like we have the length AB over R, we'd find the exact same thing because these are similar triangles.
This is a circle, wouldn't the lengths A and B equal each other?
The AB means the direct change from this point to that point. Not quite around the radius. And then the radii are the other sides of that triangle. So yes, but I'm pretty sure I didn't miss anything on this. So we're looking at the far side, this flattened arc, and then A and B are these 2 sides.
Yeah, we turned AB to R squared.
Right. Okay, so those 2 things are equal, and so those 2 are equal. Okay, and we are almost there, tantalizing. AB is our change in position. So in the book lingo, we would have that as delta S. Please don't talk over me. It is rude. Rearranging this, I'm just going to multiply both sides by V. We get a V over here times my delta S over the R. And finally, well, not quite finally, we have, just rearranging this slightly, V over R times this delta S. Now the last part here is we were looking at acceleration. Well, this is acceleration if we divide it by the change in time that it took. And we have to do that to both sides. What is a change in position divided by a change in time? That's a velocity. That's another V. So this is delta V over delta T. That's equal to the acceleration, which is equal to what we've got here, V over R times another V. So when we're talking about something moving in circular motion, we find that for the acceleration, which you probably recall from the books. I will correct my penmanship on that, because that would make it a lot easier. So we've got a couple different ways now to look at force involved and the motion of things when they're under the influence of gravity, because we know that one way was Newton's law, m1, m2 over r squared. But now we have another way, because here's an expression for the acceleration. So this would be like our m1, the object that's actually moving, times v squared over r. And we'll wait for another day to talk about a couple of specifics, I think, on this, namely the period of rotation and how long it takes and that sort of thing. But these two things are equal. This would be mass of the planet, say, if you're orbiting it. This would be the mass of whatever type of satellite is going around. These two are the orbital distance, or orbital radius. And this is the linear speed. So how fast is it going from one moment to the next? And so in that way, we can figure out a fair number of different aspects of it, and we can relate those. And I think I do want to talk about one application of that. Question?
Isn't the orbital radius only half the distance though?
No, remember this is the distance from from the center of one to the center of the other. So it would be, if we drew our circle out here, it would be the distance from that center out to the whatever is moving around, like that. And the main thing is we make the assumption that these two things are perfectly uniform and that their mass, we can say that their mass is centered at it, at the very, very center. I don't know if I want to talk about that or not. We might. Okay. Briefly, I do want to talk about one important part using this, which is how long does it take things to orbit? So it depends on the radius, as we saw, but I'm going to rewrite this and just do a little bit of math with it. So m1, I'm going to say mass of the planet. m2, I'm going to say mass of the satellite, and then r is the distance between them. Satellite squared over r. And I'm going to simplify this a little just to show us that one big revolution. So multiply both sides by r, divide by m, the mass of the satellite, and we get our constant g times the mass of the planet over the radius is equal to the velocity. But what is the velocity? It's how far does it go, or how do we know how far it goes, assuming it's a circular orbit?
Well, I was just going to ask,
Okay.
isn't v still squared?
Yes, thank you. How do we know how far it goes? If it goes around in a circle, how far does it go? The circumference. We have a name for it even. The circumference is going to be 2 times pi times the radius. We have 2 pi times the radius. And then for the velocity, we have to divide that. And the time that it takes to do that, we call a period, which we abbreviate with a capital T. This is still squared. And then sort of the last step here would be take the square root of each of those and we're solve for t. And so I think they've got it, yeah. They've got all that math done for us in the book, so I'm not going to go through all the algebra this time. I know. 2 pi to the 3/2 power r, 2 pi r to the 3/2 power over the square root of g times the mass of the planet in that case. And that will tell you, given a radius, how fast does it have to go? And this is related to the last couple of questions in the reading. The farther out it is, the greater the radius, the longer it takes. But it doesn't depend on the mass of the thing moving around. That isn't part of this. It only depends on the mass of whatever it is orbiting. Okay.